Every raindrop hitting the pavement and every molecule colliding in the air follows a hidden mathematical architecture. Chaotic individual events aggregate into a rigid and predictable geometric structure known as the normal distribution. Dropping 10,000 steel balls through a grid of pins proves that randomness is not lawless. Despite each ball taking a unique path, the collective result is always a symmetrical mountain of probability. The Central Limit Theorem states that when independent random variables are added, their properly normalized sum tends toward a normal distribution. This happens regardless of the shape of the original individual distributions. For this mathematical convergence to occur, the events must be independent. If one event strongly dictates the next, the bell curve collapses, leading to different stochastic structures, like clusters or power laws. The theorem also requires that the underlying variables have a finite variance. Systems with infinite variance, common in extreme financial fluctuations, produce fat tails that defy standard bell curve predictions. Abraham de Moivre first discovered this pattern while analyzing the probabilities of coin tosses. He realized that as the number of trials increases, the discrete binomial distribution smoothly transforms into a continuous curve. Carl Friedrich Gauss applied this logic to astronomy to account for measurement errors. He demonstrated that the most likely value of a celestial position lies at the peak of this specific error distribution. The bell curve is defined by an exponential function involving the negative square of the distance from the center. This squaring ensures that extreme deviations become exponentially less likely as you move outward. In a true normal distribution, the mean, median, and mode are all identical. This perfect symmetry means that the probability of an outcome is exactly the same on either side of the center. The width of the curve is determined by the standard deviation. A small standard deviation creates a tall, narrow spike, while a large one results in a wide, flat plateau of uncertainty. Exactly 68% of all data points fall within one standard deviation of the mean. This ratio is a fundamental constant for any normally distributed system in the known universe. Expanding to 2 standard deviations covers 95% of the total area. In most scientific disciplines, an observation falling outside this range is considered statistically significant and unlikely to be random. 3 standard deviations encompass 99.7% of all outcomes. Events beyond this limit are known as 3 sigma events, occurring less than 0.3% of the time. In telecommunications, thermal noise in circuits follows a Gaussian distribution. This white noise is the result of billions of individual electrons moving randomly, their sum creating a predictable background hiss. Brownian motion describes the random movement of particles suspended in a fluid. Because these movements result from countless molecular collisions, the displacement of the particle over time follows a normal distribution. The speeds of molecules in an ideal gas are distributed according to the Maxwell-Boltzmann distribution. While not perfectly normal, its components along any single axis are exactly Gaussian due to molecular equilibrium. In quantum mechanics, the ground state wave function of a harmonic oscillator is a Gaussian. This means the probability density of finding a particle is highest at the center and drops off normally. Human height is governed by hundreds of small genetic and environmental factors. Because these factors add up independently, the height of a population naturally converges into the iconic bell shape. Manufacturing uses 6 sigma to minimize defects. This requires the production process to be so precise that the probability of a defective part is less than 3.4 per million opportunities. Global positioning systems calculate your location with a margin of error. This error is modeled as a 2-dimensional Gaussian distribution, creating a circle of probability around your actual coordinates. Financial models often assume that the logarithms of asset prices follow a normal distribution. While real markets have more extreme events, the bell curve remains the baseline for pricing options and risk. Modern neural networks initialize their weights using Gaussian distributions. This ensures that the signals within the network are balanced and do not explode or vanish during the deep learning training process. The Gaussian blur used in photo editing and computer vision works by convolving an image with a bell curve. This mathematically optimal method removes high-frequency noise while preserving the structure of objects. The normal distribution is the state of maximum entropy for a given mean and variance. This means it is the most random and least biased way to describe a system with those constraints. By calculating a z-score, any normal distribution can be converted to a standard normal curve with a mean of 0 and variance of 1. This allows scientists to compare completely different physical phenomena. The area under the curve is used to calculate probability values in scientific experiments. A low probability value indicates that the observed result is very far from the mean of the null hypothesis. Heat spreading through a metal rod follows the heat equation, which has a Gaussian solution. Over time, a concentrated point of heat spreads out, following the widening shape of a bell curve. If you take multiple samples from any population, the means of those samples will always be normally distributed. This allows statisticians to make accurate predictions about massive populations using only small datasets. Linear regression assumes that the residuals, or the distances between data points and the line of best fit, are normally distributed. This assumption is vital for the accuracy of modern predictive modeling. In digital signal processing, filtering Gaussian noise is achieved through the Wiener filter. By understanding the statistical properties of the noise, engineers can extract clear data from extremely corrupted transmissions. In particle physics, the discovery of new particles, like the Higgs boson, requires a 5 sigma level of certainty. This means the chance of the result being a random fluctuation is 1 in millions. Biometric systems, like iris scanners, use Gaussian modeling to account for variations in lighting and angle. This allows the software to recognize a match even when the input data is slightly noisy. Weather models use ensemble forecasting, running multiple simulations with slight variations. The resulting range of temperatures or pressures usually follows a normal distribution, giving us the most likely forecast. In macroeconomics, the distribution of income often deviates from the bell curve, following a power law instead. However, short-term consumption shocks and local price variations often remain strictly Gaussian. When multiple measurements are combined, their errors propagate. The mathematics of this propagation relies on the variance of the normal distribution to determine the final uncertainty of the combined result. Monte Carlo simulations use random sampling to solve complex problems. Most of these simulations rely on Gaussian random number generators to simulate real-world noise and variability in physical systems. Psychological traits like extroversion are measured on scales that typically result in a bell curve. Most people fall near the average, with true introverts and extroverts occupying the rare extreme ends. Logistics companies use the normal distribution to manage inventory levels. By calculating the standard deviation of daily demand, they can maintain safety stock levels that prevent shortages during random spikes. Large-scale galaxy surveys show that the distribution of matter in the early universe was nearly Gaussian. These tiny initial fluctuations were the seeds that gravity eventually grew into galaxies and stars. Data scientists use Gaussian kernels to estimate the probability density of a dataset. This technique smooths out individual data points to reveal the underlying structure of the information without assuming a fixed model. A random walk in one dimension will, after many steps, result in a position that is normally distributed. This mathematical fact explains everything from the path of a drunkard to the movement of stocks. The capacity of a communication channel is limited by Gaussian noise. Claude Shannon's theorem proves that this specific type of randomness sets the ultimate speed limit for all data transmission on Earth. Algorithms often assume normality in data where it does not exist. Understanding when the bell curve does not apply is just as important as knowing when it does to prevent biased machine learning outcomes. The bell curve is more than a statistical tool. It is a fundamental law of nature. It emerges wherever many small, independent forces combine, making it the most dominant pattern in the known universe. In a universe governed by entropy and chaos, the normal distribution provides a reliable island of predictability. It remains the ultimate proof that out of infinite randomness, mathematical order will always prevail.